Oh, two right hands. That's okay. All right. Okay, so people are probably going to trickle in a few minutes late. That's fine. I'm going to run through this. I'll run through this now, and I'll run through this again later once we have other people are here. So welcome to the new world. Sorry, this is what we're living with. This is, is this everybody's first class or your second class? First class doing this? Okay. Let me tell you about this. So this is a very, so first, I'm using Zoom. Most of the people are using Blackboard Collaborate. The reason I'm doing this is the industry standard tool. When we're working, so I work in very large collaborations of scientists, and we frequently have to get together despite the fact we're on different continents. And this is the tool we use. We've used lots of tools in the past. This is the current favorite. So in the vein of trying to teach you real world skills, this one is a little bit more real world than using Blackboard, but they're basically the same. So a lot of the rules are the same. The other one is Slack, which is the chat channel I've asked everyone to join. We don't have to use it, but I have always found it very, very helpful when I'm dealing again with other people. When you want to ask somebody a quick question like, you know, when is the homework due, or how did you start number 4, or I'm having trouble with this, it's a nice thing to be able to instant message people, but not a specific person, but just out to the world, can somebody help me with this? So I always have Slack open both on my phone and on my desktop. So if you ever put a question on there, I'm likely to answer really quick if I'm not busy with something else. And other people can answer as well. So if you're just doing anything and you just want a quick, you know, ask a quick question, pinging on Slack is really a good thing. And again, Slack is an industry standard tool. Ah, there she is an industry standard tool that many organizations use. This is a really standard thing for lots of reasons. It sits somewhere between email and instant messaging. It's a nice combination.
Oh,
yeah. So that's why I'm using these tools. These are the industry standard tools. If anyone who's just joined, I'm just getting started here. A couple of so let me turn on my doohickey here. So I'm just going through a couple of bullets here before we get started. Okay, let's put that down a bit. So that's why I'm using these particular tools. I also had Dropbox set up, but I realized this is getting overloading, so we won't worry about that. A couple of the rules for working on online meetings is, firstly, turn your mic off if you're not planning on talking soon. Your mic can frequently pick up a lot of background noise, and I see everybody has done that. That's great. It's generally a good rule to keep your mic off unless you're planning to say something. And if you think you are going to say something, turn it on before you start talking, because, and this is the hard thing to get around, is there is a 2 to 5 second lag time between when I say something and you hear it. So if you have a question, it's always going to feel like you're interrupting. That's okay, right? Go ahead. If you feel like you're talking over me, that's okay. The problem is that both people start talking and then they both wait for the other person to finish, and then nobody goes, and then they both start talking again, right? It's like the thing you're trying to dodge in the hallway, except worse. This is just a problem with the medium. You just have to get over it. There is a raise hand button on the bottom of your screen. If you want to use that, you can. Also, there's a chat window. If you want to use that, you can. I had that stuff up. Now I don't have that stuff up anymore. There we go. So I can show the chat window. So if you have a question and you don't need it answered right away, or you want to ask it to the whole room, you can type it into the chat. That's fine. Or you can just unmute your mic and just interject. It's okay to interrupt me. That's fine. I won't be offended. What other stuff? So homework number 7 is still due. It's been due for like 2 weeks now. So if you can get that to me in any way, so I have it from about 5 or 6 people at this point. So you can run it through a scanner if you've got a scanner and email that to me. You can take pictures of it with your phone and send those pictures to me. If you can't do either of those things, let me know and we will figure out something else. Okay. So I'd like to get those by the end of this week so I can grade them and we don't fall too far behind. So that would be good. I have put homework 8 is up and on the web page, so the PDF is there under the homework section of the web page. And I sent out the new web page address to everybody the other night. If you didn't get that, let me know. And so that's all going to work as it was before. I just found a new host for the website. You just have to find it. You have to use the proper link to get there now. Yesterday, everybody should have gotten an email from Dr. Robertson saying that we're not going to do in the labs, obviously. So what we're going to do, and this is new to us, so everyone's going to have patience with everything. So we have these lab kits. So there's a paper bag full of stuff that we can use to run 2 or 3 weeks worth of lab. And how we're going to do this is you can walk over to the science building and pick one up, cross your name off. If you're picking up one for somebody else as well, you can cross off the name of the person you're picking it up for as well and take those kits. Please don't take more than one or one per person, because we're really at the limit of how many we have. Between you guys and the 1200 course, we're just enough stuff. We just got under the Amazon closeout window. So Amazon's not shipping to anybody who isn't like emergency needs. So we just barely got under that line. And so how we'll do this is we'll send out the instructions for what to do in the lab. You can write up the labs, and I think we're going to use something like Google Docs or something to write up the labs. So you can type up your labs. You can take pictures or draw pictures and put them into the Google Doc. And then we'll use that to grade the lab stuff. And you don't have to do the lab in the lab time. During the lab time, we'll have the Zoom chats open, these Zoom meetings open. If it's my lab, it'll be my room. If it's Robertson's lab, it'll be Robertson's room. And so that's a time you can ask us questions, but you don't have to do the lab during that time. That's just going to be the time we're available if you want. So you don't have to log in then, but that's the time that we're always going to be here to answer questions or help with homework or whatever you want. So that's not too important. Slack anytime I already mentioned. Warm-ups are down for the moment. I'm going to wait a bit. I might bring them back up. We'll see how things go. It's not the most important part of the class. I am recording this right now, and I will post the complete video after I'm done every time. So if you missed the class, there's technical problems for somebody, they'll all be available. I assume that people won't want to watch and rewatch my, beautiful presentations over and over again, but that's just in case you need it. I will point out that we are reducing the quantity of material left in the course. We've lost a week, and we're going to lose more. This just is not going to be as efficient as regular class. It's just going to be, it's just not going to be as good as a regular class for a lot of reasons that'll become obvious as we go along. So we're going to try to reduce the material down a little bit. I put homework up, but I might extend deadlines or reduce the amount of questions on the homework. Again, I'm going to play this by ear, and I really need lots of feedback from you guys how things are going. I've never taught this way. Most of us have never taught this way. Now, the rule that we have, I think most of us at Otterbein have, is that we're going to take care of you. We're going to make this work somehow. So don't panic. There are a lot of students panicking about, we got a midterm the next week, and what are we going to do? We're going to make it work somehow. We're trying not to leave anybody in the dust. So, so this isn't going to be quite as good a course as it was going to be, but we're going to do our best. So that's where we are with the class and everything. Any questions? I'm going to try to remember to take extra time when I ask about questions so that people can unmute and ask. Okay, do people have their ABCD cards or fingers? Yes, they do. All right, let's see if this works. Can I see everybody? No. B, C, okay. I have to hold it up so I can see it on the camera. I have to actually, it looks like I have to page through everybody, but I can do this. Okay. All right, a lot of E's and F's. There's a C, okay. Oh, pretty low numbers. All right, there's a couple of F's. A few people believe that they don't want to incriminate themselves. Excellent, okay. Obviously, the turn to your neighbor thing isn't going to work very well, but it's okay to unmute your mic, and I'll just be quiet for a while and let you guys talk to each other. This is a pretty small class, so I think we should be able to do this. We'll see how it goes, okay? All right, let's get started. So, so today I'm going to skip. We're going to move on from circuits. I'm not going to do Kirchhoff's laws properly. We're going to skip RC circuits, which is lots of fun and really interesting, but we just, it's just the thing that's going to have to get jettisoned. And so we're going to move on to the next chapter, which is going to be magnets and magnetism. So let's get started with that. So now normally at this time, what I do is I pass out magnets to everybody and just play with them a little bit, but I can't do that. So I'm just going to have to show you. So what I'm going to show you here, this is a magnet. It doesn't have its ends labeled. This is actually a cow magnet. There's a couple different variations of this, but the idea here is that you feed this to a cow and it collects up all the nails and barbed wire and stuff the cow has eaten by accident, and it attaches to the magnet and the cow poops it out, and it doesn't hurt the cow anymore. This magnet's got two ends, right? And everybody knows this, that magnets have got two poles, right? There's a north end and a south end to the magnet. These guys aren't labeled, but these guys, so here's two of these magnets, and they attract if you put them this end, and if I put them the other way around, they repel. They'll flip around and go back the other way. So these guys don't want to push together. They don't want, I can't push them, right? If they're this way around, then they attract. And so we label this as, so there's two different ends for every magnet. And so we label this as a south pole and a north pole. And if you have a north pole next to a north pole, they repel. And if you have a south pole next to a north pole, they attract. Now this is not, I'm assuming that everybody has played with a kitchen magnet before and understands how this works. And in your kits, there will be some little magnets. Some people have already picked up their kits. There'll be some little ceramic magnets like this, and each one has the north and south are on the faces of the magnets. So it's a little bit like positive and negative charges, right? Like charges, like poles repel. These are called poles. Like poles repel, and unlike poles attract. All right, so simple enough. Okay. Now we actually have a nice measuring device for this, which is a compass, right? So a compass is basically just a little magnet that's in here that's been mounted on a turntable that easily rotates. So what this means is you can put another magnet near it and it will follow along. So the red usually is the North Pole. So this means this is the South Pole of this magnet. So the North Pole of the compass is being attracted to the South Pole of this magnet, like this. And if I turn it around, it's the other side that will be attracted. So this is the South Pole of the compass, so this must be the North Pole of the magnet. So they're just attracting. So this actually acts as a nice meter. We could have done this electricity if we could have built a little rod that had positive charges in one end and negative charges in the other, but that's really hard to keep on there. Magnets, however, keep their charge all the time. So this is just a small, so a compass is just a small magnet, and usually it's the North Pole that's colored. So that's all a compass is. One of the other interesting things is that the compass can also tell you how strong a field is. If I slap this guy in, you'll notice that the compass needle wiggles. And if the compass needle wiggles really slowly, it's a weak magnetic field. And if it wiggles really quickly, it's a strong magnetic field. That's slow, that's fast. I don't know if your frame rate is good enough to see this. I think it should be, right? So out here it'll wiggle really slowly, and up here it'll wiggle really quickly. So you actually have, so this is actually a pretty useful device for measuring both where the magnetic poles are and how far away they are, how strong they are. Okay. So with this in mind, let's see if I can. It's a little bit better. Okay, unmute your mics and discuss.
if the north part of the compass points geographically north, then it has to have the South Pole at the geographic north.
That was my
Yeah,
It's the North Pole, right?
That's
I based mine off of geography as well,
Mm-hmm.
more than physics.
Mhm.
So let's see. If I have a, where did I put my magnets now? Oh, I dropped them on the floor. Right. So if I've got, where's the one that has some labels on it? Right. So this thing's got the South Pole here and the North Pole here. Right. So if I had it this orientation, then when I was like sitting here in the North Pole, let me see, I must have this backwards. These must be labeled backwards. So if this thing is pointing to north, oops. So this thing is pointing to north, this must be the South Pole. So it must be this picture that the needle on your compass is attracted towards the North Pole, right? If you're over here, it points north. If you're down here on the South Pole, it points like this, right? So depending on where you are, and of course the real picture is three-dimensional, but it looks something like this. So in fact, this B picture, although it's counterintuitive, is the actual real picture. We call it north because that's the way the North Pole of a compass, the north needle of a compass points. But in fact, the magnet inside the Earth is upside down relative to geographic north and south. So, which is confusing as heck, and which is why we normally don't talk about it. But nonetheless, this is the correct picture. And so we know that inside the Earth, there is something, and we can talk later about what it is that's creating that magnetic field, but it does turn out to look like that. So, and in fact, it's a little bit tilted, that the two things aren't quite the same, is magnetic north and geographic north are a little bit different. The North Pole generally is the place where the axis of rotation of the planet sits. So the planet rotates around that axis. But the place that magnets point to is actually a little offset. It's somewhere in northern Canada, northern Quebec somewhere, is actually where the pole sticks out, and the other side is off in the ocean somewhere. And so those two are rotated by, I think they're like 10 degrees or 12 degrees or something. And in fact, the magnetic poles change slightly over time. It's actually wandering over centuries. It's moving a little bit. So in our lifetime, it's moved like 1/10 or 2/10 of a degree around, which is like a few hundred miles or something around the exact location. So, of course, this is how people mostly understood magnets to work, right? Is in pre-scientific days, you had lodestone, which is a naturally occurring magnet, and they started figuring out that it pointed north, and that was a pretty useful thing to know. Now, of course, we're going to jump forward here, and we know that actually magnets obey that they have magnetic fields. And we can draw magnetic field lines just the same way we draw electric field lines. And so, and to do that, what you can do is you can just say the same thing as you did before, is that at every place in space, you can put an arrow, and the arrow there points in the direction of the magnetic field. But we already have a device that points in the direction of the magnetic field for us, and that's a compass. So if I have a whole bunch of tiny little compasses, I can take a magnetic field, and you can see the compasses will all point. Now let me see. This is. Let me zoom in here a little bit and autofocus here. So the compasses will all point along the directions of the field.
Put it downwards, like point it downwards.
Downwards? You mean towards the floor?
Like so the north didn't affect them?
You mean the Earth's magnetic field? Or you mean?
Never mind.
Okay, it's just when I had it above. Yeah, so they will tip a little bit. That's right. They can tip a little bit, so they can't really show you three-dimensionally. They can only show you two-dimensionally. I see what you were saying now. So if you look at this carefully, you can see the different compasses in different positions. So the ones that are here are sort of pointing this way and this way. And when they're near the thing, they're pointing in towards, or actually, they're pointing, let me see, that guy's backwards. So you see some of these got these really cheap compasses. They're sometimes backwards. But so these guys are all pointing sort of outwards from here, and these guys are pointing inwards from here, or backwards anyway. So if we were to draw that, if we take this away, and we just want to draw that. So let's say I've got a magnet here with a north pole and a south pole. Then if I have a compass here, the north pole of the compass is going to face away from that north pole because the south is going to be pointing towards it. I put a compass here, it'll point this way. Here it'll point this way. And similarly, these guys will point in. And if I have it over here, it'll point from, this end will be attracted to the south and this end will be attracted to the north, and those two forces balance out to make it level. And so it'll look, whoops, like that. Now if we follow the same rules that we did for electricity, which is something we're actually going to do, we can draw a magnetic field line sketch. So instead of just drawing an arrow at every position, instead we can, let me see, I'm doing this, let's do it the same way. So south, north. And so you can trace lines like this. Something like that. Oh, still not focus. So, and this is to say, if I put a magnet down there, right, the compass, and I can use the good one here, well, should always point along these lines, no matter where I've got it. Okay, I didn't draw my lines completely right. They're a little too loopy, but they'll still should follow, right? So over here it's horizontal, right? And then like this. So that's the thing. Now we want to understand, and this is what we're going to get to over the next week or so, is what makes a magnet, how do magnets work. And it turns out the answer is much more subtle than it is in the case of electricity. We'll have to get to it. So one question you can have is, and so what I'm going to do today is I'm going to show you a whole bunch of facts, just phenomena, things we know happen in magnetism, and then we'll get to why they happen later on. So one question you could ask, which may not be the obvious one, is what happens when you break a magnet? And it turns out this magnet is already broken. And so I can yank it apart. I could just destroy my feat of strength by breaking the magnet in two. And one thing you notice is that, oh, when I do that, the two ends are attracting. So let's say this guy was a north pole when he started off, and this guy's at the south pole. So then this must still be a north pole at the end with my fingers. So what's happened is I've broken him apart. And so now I still have a north pole here, and I can verify that with my compass, right? Is that still the north pole? And I have a south pole here. So here is the broken side. So this must be a north, and this must be a south again. So these guys are attracting like that. Now this is kind of neat, and one thing this means is that you never see a north pole by itself. So this is just not something that happens in nature, that you have that. Now this is very different from what we were discussing before in magnetism. Before in magnetism, there was no problem having a plus charge sitting by itself. But now it turns out this never happens. That you never, or at the very least, we have never observed it to happen, and we have been looking really hard for this. This would actually be really cool if we ever found it. We actually think they might exist, but we haven't ever seen one yet. And that's called, if we ever saw a north pole sitting by itself without a south pole nearby, that would be called a magnetic monopole. Right. Whereas this, where you have, so that's called a magnetic monopole if you just had one by itself. If you have a normal magnet with a south and north, that's called a dipole, right? But we've already seen that before. It's like an electric dipole. And in fact, if you look at this pattern, this looks a lot like the pattern that you would get if you had a plus and a minus charge, right? It's the electric field lines would go away from the plus charge, and they go like that. And then you'd also see lines that was going like that, right? So if I had two charged objects. So in fact, these two guys are very, very similar. And it turns out that the reasons for that are real. That is a real analogy, and that a lot of the rules that we have for these things are the same. Let's just quickly make sure we're all on the same page here. Matthew's making sure I can see it. All right. Okay, most people are answering A, which is the right answer. Is if I pull these two guys apart and I flip them around like this, they'll attract, right? Because if this guy's split up, if this is a north and this is a south, then if I turn them around, a north attracts a south, and so they'll attract. So when you break a magnet, you just get two magnets. That's one of these rules, and that's interesting. And no matter how fine you break it, if you just keep breaking it into pieces, you just keep getting more magnets. It's a little bit like if I have a stack of the kitchen magnets like this, right? If I pull them apart, they still want to snap together again, no matter how finely I snap them. If I cut one of these in two, the two things will again just act like two magnets. So we have that. Another thing that this means is that if I'm drawing these magnetic field lines and I break this guy apart, I'm going to see magnetic field in the join in between. So if I break these guys up like this, I have, let's say, north here, south here, north here, south here. And so I'm still going to see these field lines, right? But I'm also going to see these field lines. And you'll notice that the field lines, how they work is they point in the same direction a compass would point, which is also, is always pointing, so if I put a compass here, it would be repelled by the north. The North Pole would be going this way, right? So the North Pole would be going that way in between the two magnets because the North Pole would be attracted to the south and the South Pole would be attracted to the north, right? So if I had a little compass in there, it would be pointing that way. So the field lines always run from north poles to south poles in the same way that we had the rule that run from plus poles to minus, from plus charges to minus charges. But in between here, inside this broken magnet, you have these field lines running this way. Now, in fact, and just to give you, so to jump to something that we now know, is that this is actually happening inside the magnet as well. Is if I have a magnet like this, and I have the field lines running, is actually I can draw the field lines doing this. And this. Is that inside the magnet, the field lines are still continuing. And we know that because we can break the magnet apart anywhere and see those field lines in there. No matter how close together two parts of the magnet are, there's still going to be those field lines in there. And so we always have this sort of situation. Now, this is new. We didn't have pictures like this in electricity, right? You didn't have pictures where you had loops like this. And we're going to get to why eventually, but this is an important difference. All right, so if we follow the same rules for magnetic field lines as we did for electric field lines, where's going to be the strongest point here? Again, if you don't have a card, you can just hold up fingers. Yeah. Sorry, I can't see everybody at once, so I have to page through it. Yeah, so everyone's right. So this is going to be the strongest place because it's the place where the field, both it's close to the pole, but if we just look at the field lines, what tells us that? What about the lines tells us how strong it is?
They're
More
close
lines are
together.
moving through the point.
Exactly, right. I know the whole column response thing is a little more awkward now, isn't it? Now, another way, now the interesting thing with magnets are so much easier to work with than electric fields in a lot of ways, is that in fact you can see these electric field lines using iron filings. And how we do this, how this works, we can come back to in a minute. And everyone's seen this before, right? This is not a really surprising thing. So iron filings are tiny pieces of metal that you shaved off that come out of a grinder or something like that. And they tend to make little slivers. And if you spread them out on a piece of paper with a magnet under it or a magnet next to it, what happens is they tend to clump. And they'll tend to clump more at the north and the south poles because that's where the stronger field is. But they also tend to make these lines, which look a lot like the lines that we would draw. So you follow one of these lines around, this is one of the magnetic field lines. You can also do this in 3D. So this is a magnet. We have some of these in the stock room, but I forgot to bring them home. This is a magnet sitting in a water bath, and the iron filings can move around in 3 dimensions. And so you can see that you have these curves of the iron filings moving around like this. And so this is following the same thing as the field lines that we would draw. So you can imagine, for instance, and so here's just something to sketch in your own notes. So what would the field lines look like around here? How would these field lines look? So if we imagine what it looked like, and then the other question is, what would this look like? Right, what would those field lines look like? Now, if you remember what we had from charges, right, these field lines, the field lines can't intersect. So these field lines are coming out from the North Pole, so they must be diverging, and they must be doing something like this. And lo and behold, if you put iron filings there, that's exactly what you see, is you get this pattern where they move away and you don't have any iron filings in the middle here. If you put a North Pole to a South Pole, you see the iron filings all line up, and you actually have this very strong organization right here in between the two. So here, you'd actually expect this to cancel a little bit. If I put a compass in here, it doesn't know which way to point, right? It'd be a very weak magnetic field because you're right in the middle here, because these two fields are going to cancel out, and it doesn't point in any particular direction. Whereas here, it's definitely going to point away. It's definitely going to point away from the two, and here it's definitely point away below to these two. Whereas in here, it'll definitely point from the south to the north, and so point in one direction. So that's kind of cool. You can see the magnetic fields of iron filings. Now, at this point, we're going to want to start drawing these fields, and of course, we can just draw them as we were before, right? Points from north to south, like that. But we also need a way of drawing them in 3 dimensions. And so that's going to be one thing we're going to have to work on, because at this point we're going to have to start working because the situations are going to start getting more complicated. Up till now, we've managed to only work on a piece of paper, so we could just draw everything in the plane of the paper. But now we're going to want to know what's happening all the way around, and we're going to want to see other things. So how we do this, to draw lines in 3 dimensions, obviously a line going right looks like that, a line going left, and a line going up, and a line going down. But if I want to draw a line that's into the paper or out of the paper, I need a new tool for doing that. And we have a rule for that. What we're going to do is lines that come out of the paper that are pointing towards us, it's going to be like we're looking at the dot on the pen. So we can just draw those as a dot, or sometimes a dot with a circle. So that's like, this is the head of the pen, and that's the body of the pen. So that's a line, a vector that's pointing out of the page. If we want to draw lines pointing into the page, what we imagine is that we've got, instead of a pen, we've got an arrow, right? So you've got an arrow with a head, and it's got the feathers sitting on the sides, right? And so what you do is you draw an X And that's like you're looking down, down the length of the arrow, and the fins of the arrow on the backside, the feathers on the arrow are sticking out like that. So this is an arrow that's pointing into the page. Got it? Okay, so let's try this out. So let's say I'm going to take a magnet. Let's find one of my magnets here. I keep dropping them on the floor. Okay. So here's one of my magnets, and I'm going to turn it like this. So what I'm going to have is I'm going to have the North Pole sticking out. So this is the North Pole is up or out of the paper. And so here is my magnet. Okay. And the North Pole is sticking out. And so now what I want to do is, if I imagine the piece of paper is halfway through my magnet. So my magnet is sticking out through the paper. And so now what I want to do is draw the magnetic field in some places on this piece of paper. So I'll let you give that a try right now in your notebook. Try figuring out how you would draw the magnetic field at this place using this new rule. If you can hold up your sketch to the camera. Let me see if we can see it. If it doesn't work, it doesn't work, but let's give this a try. It's kind of eerie to be talking to a totally silent audience. Any thoughts? Stephen flashed it up, but I couldn't see it. Let's see. Oh, there we go. Oh yeah, okay, good. That's pretty good. What else did people have? Okay, Calvin's got something. Yeah, that's something. That's something, right? Now you get your pictures are pretty complete. So you know what's going to happen if this is the North Pole. The field lines are going to come out upward to the North Pole. They're going to loop around down away from us, and then they'll come back up underneath it. So we know that next to the thing, the field lines should be moving away from us. So you should have some X's around. Now here's the thing. Inside the magnet, there's also a field. What will that look like? If we remember our other picture. So what would the field look like inside here? Something like that. I could draw circles around it. So the field is coming at us inside the magnet in this plane, and it's going away from us outside. Okay. And that's right there. Now, if I were to draw it, and I was going to imagine something like this, where the magnet was like, I was looking at the magnet and the top of the magnet was flush with the paper, then I might draw something, right? These field lines might be going like this, and they'd be coming up and sloping away, stuff like that. But so we'll usually deal with nice circumstances where they're either coming straight out of the paper or straight into the paper, and so this sort of thing works just fine. And this is going to be a so this is going to be the convention we use to draw three-dimensional lines. Okay. So now clearly we've got some analogies here between electricity and magnetism. So let me ask you a question. I'm going to have, so let's say I've got some pieces of paper, and I managed to find an old silk tie and a pen that's a plastic rod. And if I let's see if it works today. It worked yesterday. But if I rub the rod against the silk, I should get a nice electric charge, and I should be able to pick up pieces of paper. So let me see, I think I can do that. If I do that, maybe you can see it. Right, so I can pick up pieces of paper with this, right? So I think this, and I believe this is a positively charged rod if I've got my signs correctly. I've got my signs correct. So here's the question.
You need to refocus.
Oh, okay. Getting used to my camera here. Okay, we've got some bets here. Some B's. Okay, a lot of people are with the B category. Let's see what happens. So I'm gonna, all right. So let's bring it here. I got nothing. Absolutely no movement. Now, in fact, if I do this and I do this really well, I'm cheating a little bit because this isn't a really good charged rod. If I really do it really, really well, it'll actually be this one. They'll both be attracted by the rod. And the reason for that is this thing is made of metal, and this is a charged object. And we know that if you bring a charged object, like a metal piece of metal, a conductor, near a charged object, it gets attracted, like the key and the piece of tape, right? Is the tape will get attracted to, the Scotch tape will get attracted to the piece of metal. So in fact, if you do this really well, what you find is both ends get attracted. But there is no effect between the magnet and the charge. That's purely an electrical effect, an electrical induction effect. There's no actual attraction between a magnetic pole and an electric charge. There's none. So, and it's kind of interesting, everybody went for B, but there's no, like, instead of A, right? Because there's no reason to believe these things other than the lines. So these electric and magnetic fields are completely different. There is nothing, they're not the same lines. There's two different sets of invisible lines in the world, the magnetic lines and the electric lines. So electric forces and magnetic forces are not the same thing. So there is no interaction between a plus and a north. There's no interaction between a minus and a north, or a minus and a south and a plus and a south. That there's no interaction.
So wouldn't that be answer C?
Yeah, yeah, that's right. Except, you're absolutely right, except there's the small effect that this thing is still made of metal, right? And you remember, if you take, do I have a piece of Scotch tape? I don't. You remember the exercise where you had a piece of Scotch tape and you put your finger near it and the Scotch tape would get attracted to your finger, right? That's because of electrical induction. And this thing's made of metal, so it would be attracted to the positive charge. It would also be attracted to a negative charge, right? So that's actually got nothing to do with with it being magnetic. It would do the same thing even if this wasn't a magnetic metal. Even if it wasn't a compass, it was just an ordinary piece of metal, would still get attracted. But
so in theory C, but actuality D.
Yes, that's right. That's exactly it. So that means electricity and magnetism clearly have got some similarities, but they're not the same thing. There's some more stuff that's different between the two as well. So which is worth talking about. One thing that's different is you can't do this with electric field. Is right now I've got this piece of I've got a bit of a magnet here, and I can put a metal thing on it, and I can attach another metal thing to it, and another metal thing to it. Right, I can hang paper clips from each other. Oh, this one's not as strong as the other one. Where's my better magnet? I don't have it. I'll use this. All right, is if I can hang. I can hang paper clips from my magnet. Now, if I take the first thing off again, right, the paper clips fall down. In fact, actually, they don't fall down right away. They sometimes take a little while. So what's going on is that somehow, for some types of materials, if I have a magnet, the magnet can change other things into magnets as well. If I have a magnet and I attach like a paper clip to it, and I put a paper clip, the paper clip sticks to it, and then another paper clip will stick to that. But if I take the magnet away, the paper clips won't attract anymore, and the second paper clip will fall off. So somehow this thing is changing that first paper clip into making it do something. So that's something new. And in fact, now you might think, now this happens for metal, right? And we know that metals are conductors. And so maybe there's some similarity with electricity there, but it turns out not to be the case. Because for instance, we know copper is an extremely good conductor, right? But it's not magnetic at all. I can't move this thing with my magnet at all. I can move this paperclip very easily, right? Or this thing, it moves very easily. Or if I have some aluminum foil, right? Tin foil, aluminum foil, absolutely no effect, right? It's not attracted to magnets at all, even though aluminum is an excellent conductor. So it turns out actually there's only a few types of metal that actually get attracted to magnets, and one of them is iron. And iron is in lots of stuff. So it turns out that it's only iron, steel, which is made mostly of iron, and there's a handful of other weird things like cobalt, and a few others like neodymium, and a few other weirdo elements that will actually obey this thing if they are magnetic. And we call these magnetic materials. Because they obey this. And so this is how the iron filings work. And in fact, what's happening is this guy is turning this guy into a little magnet with a south pole here and a north pole here. Now we've seen stuff like this though. In electricity, we saw induction, right? If you took a positive charge and you put it near a metal, you could induce a charge into it. But this is clearly working differently because it only works on some kinds of material. So it's a different kind of mechanism. And this explains the iron filings, right? So if I have my my magnet and I have a little piece of iron filing nearby, that iron filing is getting magnetized by that north side, and so it turns itself into a little compass with a south and a north, and then it aligns itself with the field. And if I put another little iron filing here, it'll do the same thing. And then these guys will attract, so they'll tend to clump. They'll point themselves in the direction of the field, and they'll tend to clump up. And so that's how you get these nice field lines being created by the iron filings. Is they're clumpy, and they align themselves. If they're a little sliver of something, they'll align themselves with the field because they'll get magnetized. So they'll align with their long side along the field, and so that's how you get these pretty pictures, which is something to be really lovely if we could do with electric fields. It just doesn't work. But there's one other really cool thing about this, though, that's not so obvious. And so this is kind of an interesting thing. So let me share a different window here. So here I've got a little movie I made in the lab the other day. Let me rewind it here. So what I've got here is I've got a stack of magnets sticking against one of the tables, and I've got some paper clips hanging from it. So what I'm going to do here is bring in a blowtorch. And you can see what happens is it drops right off. There, exciting slow motion action shot. I'll put this little film up online as well. So, and this happens to, this happens to all magnetic materials, is that when they get to a certain temperature, they stop being magnetic and they let go. And that doesn't happen with electricity. A hot metal still conducts. So this is another new phenomenon. Normally I do this in class and I always burn myself doing it. So this was actually much better. So we do not have the case, electricity is not the same as magnetism. And we use the letter B for magnetism because, you know, we're insane. Let me go back to my, so is not magnetism. Not absolutely not the same. But, and here's where it gets interesting, is there are connections between electricity and magnetism. There's clearly parallels. They clearly obey some of the same rules. There's electric fields and magnetic fields. And for electric fields, we use the symbol E. For magnetic fields, we use the symbol B. I don't know why we don't use M. I'm always been confused by that, but it doesn't really matter. We've used H, but we never used M. I think because we use M for mass or something like that, and we just don't want to get too confused. And so there's another way in which electricity and magnetism are related to each other. And that is, so we know that if I have a charge, it doesn't interact with a pole. There's no interaction if I have that. But if I have a current, it does. So if I have a moving charge, it does. So what I've got here is I've got some batteries. And this is the batteries like you're going to have in your battery kit, in your electronics kit. I've got 3 of them instead of 2 of them. And I can connect one wire here to one end of the batteries. And if I connect it to the other end, it's going to start putting a current through this wire. And the current, let me see, so this is the positive end of the battery. So the current will run out of this end and back to the other end. Now what I can do, put this on the edge of my desk here. All right, so you can see my pile of trash on the floor there. So I'm going to take one wire, I'm going to connect it to this end, and now I'm going to take a compass here, and here. So I'll attach one end of the wire to here. I'll attach the other end of the wire to here, to the other end of the battery. And now I've got a current going through that wire. And now you can see that the compass is affected by the wire. So if I put the wire over here, it points this way. If I put it over here, it points this way. If I disconnect the current, there's no effect. This is a copper wire, so it's not being affected by it. But if I connect the battery up again, now it is being affected. So there's a magnetic field created by the moving charges in the wire, but there isn't a magnetic field created by charge. So if I have a charged object, it doesn't do anything, but if I have moving charges, it does do something. Okay, so that's the next thing. So we know that current makes magnetic field, right? Because this thing is a magnetic field detector, so if it moves, we know we made a magnetic field. And you can also see this a couple other ways. If you take a rod, so this is a rod that's got charge running along the length of the rod, and if you put iron filings on a sheet like this, now you need a lot of current to do this. I've tried to do this in the past, and you need like 20 amps of current. It has to be a really, really powerful source. But you can get these magnetic, you can get the iron filings to create these rings. So this tells you what the magnetic field shape is around the wire. And it looks like, let's see, where's my other picture? It looks like this. So if I have no field running through the wire, then the compasses just all point whichever direction they were going to point naturally, maybe towards north or towards whatever magnet I have in the room. If I have a current running through it there, and the current is strong enough so it's the most important effect, then what you see is that the arrows on the magnets all point in a circle around that wire, right? So in other words, if the current is coming out of a wire right here, the magnetic field at any one of these points looks this way. So if I pick a point like right here, it'll point this way. If I pick a point right here, it'll point that way. So any place I pick, it'll be pointing in that thing. So if I want to draw this as a continuous line, and so this is the case where the current is coming out of the page. So if the current's coming out of the page right there, that's my current. Then I can draw magnetic field lines that look like this, that look like circles going around like this. Or I could draw another circle out here. Which just means if I put a compass right here, it'll point along the direction of that circle. So any place near this wire that's sticking through my page, there's a magnetic field created somewhere near it. Now, which way does it point? That requires what we call a right-hand rule. So this is the version of the right-hand rule I'm going to teach you. So if I have current running through a wire, I put my thumb along the wire like this, and then my fingers curl around the wire. And the fingers tell me which way the compass is going to point. So the compass is pointing this way. which is the direction my fingers curl. So I know that any place near the, let's get all this stuff out of the way, any place near the wire, there's a magnetic field pointing somewhere. And I know it's either pointing this way or this way. And we know which way by using the right hand rule. So you put your thumb along the direction of the current, and that means that the field will be pointing perpendicular in the direction that your fingers curl. So the field will be pointing at any point like this.
But wouldn't that mean that like wouldn't it depend on like where you have your like hand orientated on the pole?
No,
Because like
no, if you look at the compass from underneath, it still points the same way.
I know, but like you could like turn your hand like 90 degrees and it'd point in
Right.
it.
So if I turn my hand 90 degrees, that means that the current is going that way. So that would be current going to the right.
I mean, like if you keep your thumb still pointing upwards, but instead of like having your fingers this way, it'd be like this way.
Let me see. You're not on my camera right now.
I think that's still right because it continues to curve around the circle.
Yeah. So this is
Yeah.
still all. So in this case, if my thumb is pointing up, that's counterclockwise all the way around. So we know that the circle here will be counterclockwise.
But wouldn't that then like if you turn it like that, wouldn't it mean that it'd point like in a different direction from the compass if you don't move it? Or
so yeah, I can't do it because I don't have the wire here. So I have the wire here. If I put the compass here, the compass will point here. It'll point here, point here, if the current is coming out of the page. This is the closest I can get to it. Let's see if you guys get it. Let's try one. So here I've got my wire is like this. The current, sorry, like this, so the current pointing that way. So then I'm going to put a compass right here with a compass point that way, that way, that way, that way. It's a three-dimensional compass that can point any direction. Which way will this compass point? All right, unmute your mics and discuss it.
What I did is I put my hand pointing downward because that's the direction of the current. Then I curled it around, which appears to be G, according to the way I understood it.
So
Yeah.
if I put a compass here, what does that mean? Which way will the needle point?
I'd say it's A because of like where my fingers were pointing.
I just remember with the magnet, it flipped around at that point. So I don't know what it would look like at that point.
So this is
But
the magnet, right? This is the current is running. This is a wire carrying the current. So the wire is carrying a current. That means that it has the magnetic
Oh wait,
field line
there's
will
point
look
P.
like this, right? It'll look like a curve going around like that. That's the circle made around the thing, right? So it means right here. So I put my thumb along it. That means my fingers will be curling up on this side. So I put my hand around it. My fingers will be curling up, which means that right here, the magnetic field is pointing in which of these directions? Yeah.
That makes more sense. I'm going to change my vote.
Yeah, it'd be toward us at that point, but still in the direction of G, right?
Well,
Yes, so the overall direction will be G, but at that specific point, it'll be going at E because it's coming towards
Right.
us.
So
Okay.
right. So at any point there, the compass can only point one direction. A compass can't point in a circle, right?
Yeah.
So these are always going to be bad answers. Because if I'm asking which direction it's pointing right there, that's a single place, and you can't point in multiple directions in one place. So it has to be one of these answers. And the right answer here is E, is it's sticking out of the page. Okay, let's try this again. Let's assume you have a current carrying wire, a stick, okay? And imagine the stick is over your head and it's carrying current away from you. So the current is going in the direction of your nose. So in front of your face, point in the direction of the magnetic field. Normally in class, what I do is I'd wander out into the room and have everybody point, but we can't do that. So I'll do this. So imagine you have this thing is over your head. It's pointing along, the current's going along the direction of your nose. And so in front of your face, point in the direction of the magnetic field. Everybody has to look like an idiot. This is a rule, right? So the right-hand rule, you have to put your thumb along the direction of the current. And so my thumb is pointing along the direction of the current, meaning my fingers are curling around underneath to the left, to my left. So I should be pointing my finger to the left under my nose. So everybody should be looking like this. And of course, if you've got the mirror image turned on, then you're hosed. And if you've got, right, and you have to imagine what it looks like to other people. So from your perspective, right, I should be pointing that way. Everybody does everyone feel like they have this? This is going to be like the hardest thing to teach. I realized this morning. This is going to be like the hardest thing to teach by camera. So this is, and it turns out this is actually the most, like one of the two most important facts about magnetism is that a wire carrying a current creates a magnetic field nearby that points orthogonally to the direction of the current, orthogonally to the direction the current is going in the plane that you're looking at. So here it's pointing this way, here it's pointing this way, here it's pointing this way, here it's pointing towards me, towards me, towards me. We will practice that again at some point. So we know that, how are we doing here for time? I can't see my clock on my screen. Why can't I see my clock? Because I've got my thing in front of it. Okay, so we're coming up on time here. So we know that charges don't create magnetic fields, but currents do. We know that there's some similarity between electricity and magnetism, but they're not the same thing, that we don't have charges and poles don't interact. There is another question. So we know that we have currents create fields. Here's another question: can currents feel fields? And the answer is yes, they can. So if I get, and this is something you guys are going to be able to do with your kits. If I take a magnet, so this is a very strong magnet with a dot indicates the north pole of the magnet. And I'm going to take my wire here again. So I'm going to have, let me see. So the current is going to run from the top down to the bottom when I connect it. And so what I'm going to do, let me back up here so you can see what I'm doing. So I'm going to put my magnet over here, and I will hold it very gently in place here, so I'm not moving the wire around. And so when I connect the wire, it moves very slightly. I don't know if you guys can see that. It's hard to see, and I don't want to hold the wire too still because then it can't move. No, you can barely see that. Maybe if I hang the wire over it. So if I hang the wire over it like this, and then I connect it, there you can see it. Connected, not connected. Connected, not connected. Connected, not connected. And when you do it yourself, this will be much more obvious.
Is that supposed to like do with like, you know, like those magnetic locks?
Yes. So this is going to lead, so these two phenomena, that currents can create magnetic fields and that currents can feel magnetic fields, lead to a whole bunch of devices that are going to be very important to us, including a solenoid, which is what a magnetic lock uses. So this is electromagnets, solenoids. This also leads to electrical generators and electrical motors, which is going to be one of the ultimate goals that we're going to lead up to, is how did those devices work in terms of their physics, which of course might be important for someone who does, engineering and building things. So the principle, so that's ultimately what we're going to be getting to in the next few weeks, is how those devices work, and they depend upon these basic phenomenologies. So we know that current can make a magnetic field, and we know that B makes a force on a wire that has current. So those are the two rules we now know about the connections between electricity and magnetism. Now, which way the wire moves in this case, that's another right-hand rule, and I'm going to come back to that. This is just sort of a prelude to stuff we're going to cover later on. Okay, this I think is a good place to end for the day. Let me just go back over some review here. I'm recording this lecture, so if you missed part of it or your sound wasn't working, you should be able to come back and see it again. There's no warm-ups yet, but it's pretty clear what chapter we're on, and so I advise you to start reading the magnetism chapter. I forget which number that is. So read the magnetism chapter. We're going to start on next time is magnetic flux and the meaning for that, and looped magnetic fields. If you have any questions at all about anything, hit me up on Slack, either on the general channel or in the channel for our specific course. If you hit the general channel, that's everyone who's taking physics. If you hit the course-specific channel, then that's only you guys. Homework 8 is up. There's a PDF you can print off the web page, which I sent around. And make a plan to go in and pick up your lab kit sometime in the next couple of days. The science building is open, and you just have to go in and grab one paper bag and cross your name off the list. And we'll be circulating instructions for those kits soon.
So is it in your office or by the lab?
So it should be by the intro lab on the second floor.
In Slack, it also shows me in Davis's course at 1200.
So you can just exit from that. You just got added by accident.
Oh.
So you can take yourself out if you want, or you just ignore it. It's fine. I'm attached to so many Slack channels at this point. I don't even look at half of them. They're just noise. That's one of the downsides of email and Slack, is you get a lot of junk, right? You have to sort through. But it's still good. I am reducing topics, and please find a way of getting homework 7. Is there anybody who thinks they don't have a way of getting me homework number 7 at this point? If so, shoot me an email, and everyone's email should be working at this point. Well, you wouldn't be on here if you couldn't get email, because you wouldn't know about it. And if you're having any problems, so one of the things I want you to do is, if you get sick, let me know, let your professors know. This is going to happen. Some of us are going to get sick. If I get sick, it's really bad. If you get sick, it's really bad, right? So let us know if there's problems. Let us know if you have connectivity problems. If you're running this on a phone and you don't have enough bandwidth, let me know, and we'll try and find a workaround so we don't use your whole data plan. We're going to try and make this work for you guys through this whole thing, and we want to give you the best education we can under these conditions, and we don't want anybody to go, needy as a result. Okay. So if you have any questions at all, hit me an email, hit me on Slack, and we'll try to answer those. I think today was pretty good. On a scale of down thumb to up thumb, not too bad. Could be better. I'll get better at this as we go on. And if you have any suggestions or thoughts or questions on any of this stuff, let me know. And I will see you guys on Friday. Okay? So stay safe. Wash your hands. I know everyone's sick of hearing that. And have a good day. I'll see you guys later.
You too.